Hello, hello, hello. In this worked example, we're going to consider a problem I call Atwood on an incline. We consider this situation here, which is sort of a modified version of the Atwood machine that we've previously considered, where you have a frictionless pulley and two different masses, and the thing is free to accelerate, but the twist in this problem is that one of the masses, mass A here, is located on a frictionless inclined plane. And what we'd like to do now is use our principles of energy, and in particular the energy principle and conservation of energy, to answer the following question. We assume that mass B is the greater mass. It has a mass of 2 kilograms. Mass A is only 1 kilogram. The inclined plane has a angle of 30 degrees, and we just want to know how fast the masses are going to be moving after mass B has fallen by a quarter of a meter. They've got to be moving at the same speed because there's a fixed length of rope between them. So let's get to it. So if we're going to use energy principles, we want to get in the habit of defining our system. I'm going to put a dotted line over here. And as part of the system, I'm going to include the Earth because we're going to be making use of the gravitational potential energy of the system consisting of the Earth and this assemblage here. And we'll consider our system to be an isolated system, no interactions with the outside world, so that the total system has an energy which is conserved. So as the masses move, the total energy of this system is not going to change. And then let me define a axis here. We'll call this the y-axis, and we'll let y equals 0 be the initial elevation of mass B. And in the final configuration that we're going to consider, mass B will be located at an elevation of with a y value of minus 0.25 meters, corresponding to the fact that it will have fallen through a distance of a quarter of a meter. And now let's write our statement of conservation of energy. Let's break it into two parts. The left-hand side, there's going to be a change in the potential energy of the system and a change in the kinetic energy of the system. But these changes have to add up to 0. Okay, now in the initial state of the system, which is shown in the picture here, the potential energy is due to the potential energy of the two blocks. And we won't lose any generality by assuming that block A and block B are both located at y equals 0 in elevation. So I'm going to write the initial potential energy of the system as ma times g times ya initial plus mbg times yb initial. And we're assuming that both mass A and mass B have y coordinates initially of 0. So the initial potential energy of the system is 0. And also, we're assuming that the masses are at rest initially, so the kinetic energy of the system is also initially 0. So the total, we've defined things so that at the beginning of the story, the total energy of the system is 0, and it's not going to change, so the total energy of the system will remain equal to 0 throughout the motion. Okay, now in the what we're going to call the final state here, mass B has fallen by 0.25 meters, and of course mass A has moved up the slope by a distance of 0.25 meters, and now there's some kinetic energy in this state. So let's write down what the total energy in the final state is going to be. Okay, so let's start with the potential energy in the final state. The potential energy in the final state is going to be, have two contributions. One is from mass A, And that contribution is going to be whatever mass A is, times G, times the Y coordinate of mass A in the final state. That's this value here, which we don't yet know. We have to apply a little bit of trigonometry to get that, but we'll do that in a moment. And then we have, of course, the contribution from mass B, which is the mass, whatever mass B is, times G, times the Y coordinate of mass B in the final state. And we know right off the bat that that is minus 0.25 meters, right? That's where mass B is in the final state. Okay, and then here's where the little bit of trigonometry comes in. How much has mass A risen in elevation? Well, if you look at the triangle here, you'll see that mass A has risen by less than a quarter of a meter because it's on a slope. And so you should convince yourself that the Y coordinate of mass A in the final state is given by 0.25 meters times the sine of this angle theta. And then we have a minus mBg times 0.25 meters. And now you'll notice I've avoided plugging in our numerical values just because it's easier to not do that till the end. And now it's time. We know what mass A, mass B, and theta are, so we can plug in those numbers here. We know what G is, and I'm going to save some writing and just tell you what the numerical answer is. We find that U sub F, plugging in, is equal to, and we end up with a numerical value for the potential energy in this final state of minus 2.45 joules. And we're almost done here. We know we've argued pretty convincingly that the total energy in the final state has got to remain equal to zero. So what does that mean? That means that the kinetic energy in the final state must be equal to plus 2.45 joules, and that's equal to 1/2 times the total mass. Both masses A and mass B are moving, so there's a total mass of 3 kilograms times the final speed. They have the same speed, so there's just one unknown in this equation, the final speed of the system, which is what we're asked to find. So now we just have to plug in and solve for that numerical speed. And we find, just solving for V sub F, it has a value of 1.27 meters per second. So that is the answer to the question that was posed, and that's it for this worked example, Atwood on an incline. Hope to see you again soon. Bye-bye.